Okay, this is Poiseuille's law. Poiseuille's law, or the Hagen-Poiseuille's equation, is an essential part of understanding how blood flows through tubes, and it's of particular importance, especially in regards to cardiovascular physiology. So it starts with a few very basic precepts. So you need to start thinking about flow in tubes as a result of pressures, and you can think of pressures as like in electricity, a pressure would be the energy difference between the beginning and the end of the tube. So this thing here is, or the first line of the equation on the left is the notation for flow, and flow is in volume per second. And one way of knowing that is area multiplied by velocity, and that will give you the flow. But there are a number of factors that can influence area, and a number of factors that can influence velocity, and we're going to be thinking about the derivation of Poiseuille's law, and we're going to be using this to effectively derive. We're going to try and derive Poiseuille's law through a series of first principles. Now, the first thing that we're going to consider is a tube, which is going to be our blood vessel, or we'll consider it as a cylinder. So here's its one end, view it. So this is like the open end of a Pringles tin, and this is the far end that you cannot see. And inside this, we're going to have another tube. And this other tube is going to extend down across here and finish up down the far end. Okay, so just going to fill the central tube in. There you go. Right. Quick change in colour. Now there is going to be a pressure going this way, and there's going to be a pressure that wants to stop the blood from moving. So we're going to call this P, and we're going to call this one P plus delta P. And so the net force acting on this tube is in this direction here, and obviously pressure is equal to force per unit area so now we can denote this as delta P. We don't know the force acting, but we do know the area that it's acting across. If we say that from here to here, we're going to know as R, and this will allow us to predict how big the tube is. And now we're going to have this inner tube here, and we're going to say that this inner tube is going to be of width x, and the x is, we're going to define it as less than or equal to r, and greater than or equal to 0, depending on how we want to view it throughout the course of this experiment, of this thought experiment. So we're going to go back to A. A is this area here that the pressure is acting upon, and this is known as the area of a circle. So simple GCSE stuff so far, it's all good. Pi r squared. So now what we're going to do is we're going to move down the page slightly. Let me just take this and remove that. Now, so we had delta P is equal to force divided by area. So then we can take the area, take it up to the top, cancel that round from there, and so then we can say that force is equal to delta P times pi r squared. There you go. And now we can get rid of that, and also get rid of that. Okay, so obviously we've got a force which is created by the pressure of the fluid, but then the question would be, is that if there is a force according to Newton's second law, we're going to assume that the blood is going to be flowing at a constant rate. It means that there must be an opposing force. So we're going to say that this is the force from the pressure, but then we're also going to say that there is a force, a secondary force, from the viscosity. Now, viscosity, at least in this instance, is the interaction between the planes of fluid. Oh, just get rid of that. So, and this is just dealing with the shear forces that exist between the different planes of fluid. So, if I just illustrate it quickly, so you have this here, and this is the velocity is equal to 0 here. This is acting as the wall, and this one here will have a velocity of delta v, because unknown velocity, and this unknown velocity, between these two here there will be an interaction, so there will be a resistive force between the two, which will pull this one this way, which will stop it shooting off, gaining an increase in speed beyond that which it's the force of this one here, this force here, will allow. Okay, so what factors can affect the force of viscosity? So we're going to put that equal here. Now that there is there's going to be a if you increase the length of the tube, then you'll get an increase in viscosity, or the force acting. So we will denote the length of tube as L. The area that the force acts over is also significant. In this instance, it's 2 pi r and that is the surface area, or the circumference of a circle. So the surface area of a cylinder will be L times by 2 pi r. Now we also have we have to take into account of the change in width of this cylinder that we're talking about. So and also the change in velocity. So obviously, as the velocity goes up, the frictional force will go up, and as the velocity goes down, the force will go down. So we're going to denote that as dV. There is also the width of the column. Obviously, r can change. But r isn't actually the thing that we're interested in. I'm just going to change the notation that I've used here. I'm going to change that to x, just like in the original, just so that there is no confusion. So 2 pi x, and also we get here 1 over dx. And then finally, we actually have the degree of interaction between the two laminar sheets of fluid, and that is known as the this here is a measure of the dynamic viscosity. Dynamic viscosity is very important to consider. So then, effectively, then what we can do is we can say when these two forces are equal to each other, velocity will be equal to 0. There will be a constant speed. So when we put them together, we end up with, when we've rearranged it, we can make dV by dr we can make dV by dr the subject of the equation, and this is quite important, because this allows us to now convert this into a differential equation. So by simplifying out, we get delta P divided by 2 So I've just realised I've used non-standard notation. Sorry, go back down. Standard notation for viscosity, as opposed to mu, which I was using. So then we get this, and this is the first major step for the calculating of the Poiseuille's equation, or the derivation of, because we can convert this here by multiplying the right side by dr, so we can cancel that off this side. We can then integrate both sides, and then we can integrate this side as well, and then we'll look at the end result of that. So we'll just quickly get rid of that. Get rid of that. Okay. So we're now gonna jump forward a few, and we're going to be looking at the integration of what we have. So what we end up with is through integration, we end up with V is equal to delta P over 4 dynamic viscosity constant L, and this is a constant here. This will not change because it doesn't have a function of R in it. And then we have R squared, which is the radius of the entire pipe, minus x squared, which is the radius of our small column of fluid. And this will have a parabolic form, as would be predicted from such an equation. Now, as I mentioned before, flux or volume or the flow is equal to change in volume per change in time, and that, as I mentioned before, is equal to, at any given time, is equal to the viscosity multiplied by the area. However, we would want to know the total variation, because obviously there can be variable speed and variable area. So we will want to be summating the volume and finding out the change in the area. So then we can substitute this equation into this one, which involves us integrating again. So we integrate v, and we multiply that by dr, or by dx, and this will result in us getting a very clever little equation. So I'm just going to quickly put this out. Okay. So we get pi delta p divided by 2 mu, it's not mu, sorry, again, same mistake. Dynamic viscosity constant multiplied by L, and then this multiplies by r to the 4 over 2 minus r to the 4 over 4, and these simplify down to r to the 4 over 4. And then, if you multiply this by this, I'll just simplify this down here. If you multiply the 4 by the two dynamic viscosity constant times L, you end up with 8. And then if you multiply the top by r to the 4, what you end up with is Poiseuille's law.